Hello everyone. So today we are going to start with chapter number 1, real numbers, a very important topic of this chapter, and that is proving of irrationality of numbers. So you all must be aware about what do we mean by a rational number. Let us revise the definition once again. A number R is said to be a rational number if it can be written as P upon Q, where both these P and Q are integers, and the most important thing is that Q is not equal to 0. So this is the basic definition of a rational number. So now we are going to do proving of irrationality of numbers. Let us see. Suppose we want to prove that root 2 is an irrational number. So what we are going to do, root 2 is an irrational number. This is what we need to show. So let us first discuss some basic facts which we are going to use in this. There is a theorem, and that theorem says that let P be a prime number. Let P be a prime number and A be any positive integer. So A can be any positive integer and P is any prime number. So the theorem says that if P divides A square, then P will also divide A, and P divides A also. So let us see this with an example, then you will understand better that how to apply this in the questions. See, let P be a prime number. So let us take any prime number. P is equal to 5. You all know that 5 is a prime number. So 5 is dividing square of any number. Suppose 5 is dividing, we say 625. 5 is dividing 625, and 625 is actually 25 square. So if 5 is dividing 25 square, will 5 divides 25 also? Yes, the answer is yes. It is dividing 25 also. So that's the theorem. Koi prime number, if there is a prime number which is dividing a square of any number, then it will divide that number also. So this fact will be used now in this question. Let us see how to do this. First of all, we will be using a contradiction method. What is that method? We are going to assume that root 2 is an irrational number. So let us assume that root 2 is a rational number. So if root 2 is a rational number, then as per the definition which we have just discussed, then root 2 can be written as P upon Q, where P and Q are integers. P and Q are integers and Q is not equal to 0. One more thing, suppose we have a fraction, suppose we have 5 upon 15. So can we not divide it further? Can we not cancel it further? It can be 1 upon 3. And what about 1 and 3? 1 and 3, they cannot be cancelled out further. So 1 and 3 are basically called co-prime numbers. The simplest form of this, if we convert the fraction into the simplest form, the numbers which we are getting are called co-prime numbers. So basically co-prime numbers are numbers whose HCF is equal to 1. Okay, that also we can say that HCF of co-prime numbers is equal to 1. So here only when P and Q are co-prime and P and Q are integers, and Q is not equal to 0, we can cancel out and we can say that P and Q are actually co-prime also. Okay, so P and Q are co-prime also. This is a very important fact which will be used later on in this proof. Now if we cross multiply here, so it will be root 2Q is equal to P. So on squaring both the sides, we have this root. So to remove this root, we will be doing squaring both the sides. So we are getting 2Q square is equal to P square. And from this statement, because 2Q square is equal to P square, we can say that because P square has been written as product of two numbers, so we can say that 2 is dividing P square. Now 2 divides P square. From that theorem, 2 is a prime number, P is any integer. Since 2 is dividing P square, so we can say that 2 divides P also. So 2 is dividing P also. So 2 divides P square, we are getting 2 divides P also. Now what's the meaning of this? Let us elaborate this once again. P can be written as 2 into R, where R is any integer. So this is the meaning of this, that it is dividing P. So where R is an integer, P has been written as 2R, where R is an integer. Now let us put this back to the first equation. This is the first equation. Let us put this back to the first equation. Put in first equation. So what we are going to have? if we put this in the first equation, we are going to have 2q square is equal to p. In place of p we put 2r whole square. Let us simplify it further. If you simplify it further, what we are going to have, 2q square is equal to 2r whole square, so it will be 2q square is equal to 4r square. That means q square is equal to 2r square. So now see this statement once again. We were getting, earlier we were getting p square is equal to 2q square. Now we are getting q square is equal to 2r square. Aren't they similar? So what we are going to have from here? Here we were having 2 divides p square. Here we are going to have 2 divides q square, because q square has been written as product of these two numbers. So 2 divides q square. From this we are going to have 2 divides q also. So now see what we have shown. By doing all this, what we have shown, that 2 was dividing p, one thing, okay, 2 was dividing p, and 2 is dividing q also. So now we are getting that p and q are having 2 as a common factor, but that thing is a contradiction. Why? Because earlier we have said that p and q are co-prime, they cannot be cancelled out further. Like here we were having 1 by 3, they are co-prime, they cannot be cancelled out further. So these two things are contradictory to each other. So what we can write now, we can say that p and q have at least 2 as a common factor. 2 is a common factor in both p and q. We have at least 2 as a common factor. There can be more factors also, but at least 2 is there, that we have just shown that 2 is a common factor to p and q. But that thing is a contradiction. Which is a contradiction? Why it is a contradiction? As p and q were assumed to be co-prime. They were co-prime. As p and q are co-prime. So since they are co-prime, they should not have any common factor, but it is actually having 2 as a common factor. So these two things are contradictory to each other. So it means that our assumption, therefore our assumption, what was our assumption? Our assumption was that root 2 is a rational number. Assumption is wrong. And since our assumption is wrong, this assumption is wrong, that it is a rational number. So agar rational number, it is not rational number, so it means that so root 2 is an irrational number. Okay, so we have just shown that root 2 is an irrational number by this method, which is called contradiction method. And in fact, this year in board exam, a similar question was asked. It was proved that root 5 is irrational. It was asked in one of the sets that prove that root 5 is irrational. So the same thing will go for this question on also. It is just the same thing. In place of 2 we will be having 5. Okay, and the entire question, the entire solution will be exactly similar. So you can now pause the video and note down and do this as your homework question. Thank you.